Hello, everyone, and welcome to the October edition of the Rust Formal Methods Interest Group. Today, we're going to have Professor Hui Xu, who's going to talk to us about taming unsafe Rust with safety tags. Take it away.
Okay, thank you, Jonas, for hosting me. Okay, I'm Hui Xu from Fudan University. Okay, it's 2 a.m. at Shanghai, so I will try my best to present the whole idea clearly. Okay, so today my presentation topic is taming unsafe code with safety tags. So in this talk, I will introduce a new paradigm for understanding unsafe code and prove the soundness of code without undefined behaviors. First of all, let's review the background. So currently, Rust is unable to provide any safe guarantee related to unsafe code. The best practice is to use safety comment. That is for the unsafe, sorry. That is for the unsafe function declaration, the developers should provide the safety comment to indicate how to use the function safely. And in the call set of the function, then the users should specify why using the unsafe function is safe. So this is a current best practice, but it is informal and can provide almost a non-guarantee. And currently, the community is the effort of the community is to do some formal verification based on especially based on the model checker. In formal verification, we provide a contract which include the precondition and post conditions, and we can then use model checker to prove the correctness of the function implementation. However, the formal verification is generally heavy because it requires to annotate the contract. So our research vision is a lightweight yet formal approach. We have a group that work on the project, including 2 PhD students and several master students. Okay, so today my presentation will include these 3 parts. In the first part, I will introduce the idea about safety tag, which is used to annotate the safety requirement of unsafe functions. And in the second part, I will introduce a new theory for verification based on safety tags. And finally, our current verification practice based on RAPx. Okay, let's review the current comment-based. So this is the current practice is based on a comment-based approach. That is, at the unsafe function declaration, the developer should specify the safety requirement, and at the call set of the unsafe function, the user should justify why the use of the unsafe code is safe. But such practice have several issues. Firstly, the consistent issue, like the missing safety requirement declaration, and some specifications are inconsistent. And our group already fixed several such issues in the standard library. And the second issue is ergonomics, because the safety comment, there are many repetitive safety comment across functions, and they have extensive text. Okay, so it is difficult to maintain. And the last issue is the precision. Obviously, safety comment are not as precise as a contract. So these are the issues of current safety comment approach. We propose a new approach based on the safety tags. There are 2 versions. A basic version, which means a safety tag is an abbreviation of the safety comment. We implement the safety tag as Rust attribute, and they can be compiled into docs so that the current users will they can still enjoy the old way to read the safety comment of unsafe function. Okay, there is also an advanced version which is more precise because the safety tag can have parameters. So the safety tag in this way can become a safety constraint in a domain-specific language, and it can be translated into contract. The basic version currently we have submitted RFC to the community, and it is currently under review, and we have received many positive feedbacks. So let's use one case to demonstrate how to use safety tags. Okay, where is my mouse? Okay. So for safety tags, as a unsafe function declarations, instead of using safety comment directly, here we provide the safety tag like align, which is an abbreviation of alignment requirement. So we use safety requires. And as a unsafe function call set, we should discharge the safety tag. So in this case, we specify we say the alignment requirement is already checked, so it is safe. There are three ways to discharge safety tags: checked, delegated, or transformed. For delegated, it means the function has done nothing regarding the safety requirement. So the safety requirement is directly delegated to the caller. So the caller requires the safety tags. And the last situation is transformation. If we slightly modify this example with if s is greater than 0, then we call the unsafe function. Then we can transfer the previous alignment safety tag to a valid number, because if x is smaller than 0 or equal to 0, then the unsafe function is not called. So either align or a valid number can satisfy the safety requirement of the unsafe callee. So this is a general idea of the basic version of safety tag. The safety tag, although we only declare, we only use the name of the tag, but we can provide descriptions, full description of the tag in a TAML file, so that this text can be reused. And when compiled, the tag can generate docs. Okay, and we use this example for demonstration. This example, we have unsafe function full and a call set. However, we done nothing regarding the discharge. So we can write some static analysis script to declare, to check that it is not discharged. So we give some warnings or errors to developers. We can further use the cargo expand to see what happened, because we implement the feature through procedure macro, so that the safety tags are expanded to docs and contract. Let's watch the example again. So here, safety tool give error or warning. And when we run cargo expand, it expand to RAPx, contract, and docs. Okay. Now we see with safety tags, the first consistency issue can be solved, missing safety requirement, because we can check whether with procedure macro, whether all the unsafe function have safety requirement. And if some unsafe function has no such attribute, then we can give a warning or error. And the ergonomics, now we can use very short safety tag. and we can reuse a comment. So this issue should be solved. And for the rest two issues, they are actually related to the contract. So we will discuss the advanced version of safety tags. Remember that safety tag can be compelled to doc or contract. So what contract do we support? We support two types of contract related to contract, but not exactly contract. So the first type is precondition, which is the same as the precondition of contract, which means a constraint that must be satisfied when calling the unsafe function. And the second type is hazard, which means the constraint cannot be, satisfaction cannot be checked at the current stage when calling the unsafe function. So it may temporarily leave the program in a vulnerable state, and the hazard should be eliminated. Let's use this example, PTR read, to demonstrate what are preconditions and what are hazards. Okay. For this unsafe function, under the section of safety, the first sentence is SRC must be valid for read. So it's a precondition, a precondition of valid pointer. Okay, so we can represent this one with the safety tag. And the second sentence is SRC must be properly aligned. So it's also a precondition, which means the pointer as SRC, which is the argument, must be aligned with respect to the type T. In the third statement, we can use init pointer T1 to represent this safety requirement. Under the section of ownership or return value, there are also some requirements. For example, if T is not copied using both the returned value and the value at star SRC can violate the memory safety. It's not a prerequisite, a precondition. To only give some warning to use the returned value, how to use it safely. So it's a hazard because PTR read can introduce alias if T is not copied. So we represent this safety tag as a hazard. And this hazard can be eliminated if T is copied. So if T implement copy, so it can remove the hazard. So let's compare what's the difference between safety tag and the contract, especially the post condition. So contract has post condition, while safety tag do not. Post condition for contract are often used by the function with interior unsafe code, and we provide post condition at the end of the function. So when time of use, it introduces hazard. When it leaves the function, we should check whether the hazard are eliminated or the post conditions are satisfied. However, for safety tags, we do not use post condition. We only need to check whether the hazard are eliminated automatically. So we don't need to annotate post condition. They can be automatically done. In this example, S2 is a return value of PTR read. It is dead before the function returns. So the only live reference is S to the object. So the hazard is eliminated. Now, the precision issue seems we can solve. Maybe it's not as precise as contract, but we can already make it to have some formal semantics related to the safety requirement. Also, if the safety comment, if the safety tag can formally represent the safety constraint, we can verify. We can also verify the consistency of the safety tags because the verification of can also be used to check the consistency of safety tags. It's the same thing. Now we have a question: is it possible to represent all safety constraints as tags? In the previous example, especially for transformation, safety tags can be transformed to different to other tags. And theoretically, we can have these safety constraints are Turing complete, so it might be difficult to represent with only tags and parameters. But we are optimistic. Why? Because we can have numerous safety tags, and each crate can define their own safety tags. And remember that safety tags are abbreviations of safety comment. Currently, practice have already proved that it is possible to use safety comment. So it is possible with safety tags. Because programs, they are not random, they are meaningful. So we can represent this requirement with safety comment. And the main challenge lies in the precision. That is, if the comment can be extended or expanded to contract, whether our safety tag can be extracted to contract, whether their representability are equivalent. So this is a question. We are currently conducting experiment with these three projects. The first one is Rust standard library. We have almost annotated all the public APIs within the standard library, and the coverage can achieve over 19%. And we are also starting working on Rust for Linux. It's very complicated because there are operations with C original C part. So it's very challenging. And we are also working on another operating system, Asterinas. It's written in pure Rust, so it's a bit more easier for us to do the annotation. And we are currently achieve a coverage of roughly 15%. Okay, so this table shows the safety tags we proposed for the standard library. There we use 23 tags to annotate about 19% of the Rust of the public APIs in Rust standard library. Okay, now let's go to the second part, which is a new theory for verification based on safety tags. Our new approach is based on a theorem that related to the origin of undefined behavior. In the theorem, all the undefined behavior originates exclusively from unsafe code, and it is only determined by the safety constraint of unsafe code. This is true, but we have to show that it is true. For the first sentence, we can show it is true based on the safety promise of Rust. Soundness means well-tapped program cannot cause undefined behavior. The promise only extends to safe code. However, for unsafe code, it is up to the program to uphold the contract. We can rephrase this sentence into the following two sentences. Safe code cannot cause undefined behavior, and only unsafe code may exhibit undefined behavior. So the first clause of the theorem can be proved. What is the meaning of the second one? UB is solely determined by safety constraint of unsafe code.
Could I perhaps intervene, Hui, or would you prefer that we leave questions to the end?
I don't know. I don't see a reason why you couldn't intervene. Maybe depends on Professor Xu.
Okay. I think I will. I think at the end, after 45 minutes, is that okay for you?
All right. I'll keep my question until then.
All right, okay. Then let's wait until then. Sorry.
Okay. So we can represent the first part of the theorem in this way. For all the programs that use the function, the safe function f, so the program should not lead to any undefined behavior if the program does not use contain unsafe code. So how to define the soundness of unsafe function? We should recall the interior unsafe code. if the function is safe and it contains unsafe code, it should prevent all the potential undefined behavior of the unsafe callee. So the developers should provide all the safety constraints of the unsafe function, and they should be sufficient condition to prevent all the UB. So this is a requirement. And based on our observations from Rust standard library, this safety comment have two characteristics. The first one is pervasiveness, which means each unsafe function has such a set of safety constraints which are sufficient conditions to prevent undefined behavior. And the second characteristic is uniformity, which means safety constraints are applicable to all context of call set. So we can represent the two characteristics in this way. For all unsafe function FU, there exists a safety constraint for the unsafe function such that for all programs that use the unsafe function and the program satisfies the safety constraint of the unsafe function, the program will not lead to any undefined behavior. So such safety constraint should exist. Then, based on this observation, we can define the soundness criterion for unsafe function. So unsafe function FU it has safety constraint FU. So it is sound if for any program that calls FU, it contains no other unsafe code. If the safety constraint of SU is satisfied, then PFU does not cause undefined behavior. So this is the soundness criterion of unsafe function. Now the theorem can be, the second clause of the theorem can be proved. How? Because we can assume unsafe function FU with safety constraint is sound. And we also assume a function that uses FU and satisfies the safety constraint, but the program leads to UB. So this leads to a contradiction. So it can show that UB is solely determined by safety constraint of the unsafe code. And based on the theorem, we can derive some rules for safe encapsulation. We first derive rule for the safe function encapsulation. If fs contains no unsafe code, it is a safe function and has no unsafe code. Obviously, it is sound. If it contains unsafe call set, then for all the unsafe callee, the function should make sure the safety constraint of the unsafe callee should be satisfied. If the function is unsafe and it contains unsafe callees, the safety constraint of the unsafe function and the function itself should ensure the safety constraint of its unsafe callees are satisfied. We can unify the two encapsulation standard into one by treating a safe function with empty constraint. So we say a function is sound if for all the unsafe callees of the function, the safety constraint of the function, given and the function, the safety constraint, all unsafe callees are satisfied, we can ensure the soundness of the function, no matter it is safe or unsafe. The next question is, can we extend the previous theorem and encapsulation soundness approach to struct? Struct is more complicated because it has a static method which is similar to the previous function, but also dynamic method. We should compose an instance of the struct first through the constructor and then call the method. So the constructor may also contribute to some safety insurance related to the safety constraint. And the method safety declarations are more flexible. We will give examples to show the flexibility. And method with a mutable self parameter could affect the soundness of encapsulation of other method of the struct. In this example, we would like to show how the safety declaration of function of struct method are flexible. This struct contains two fields, a raw pointer and a length field. And the constructor from is safe that accept raw pointer parameter and length. And it has two dynamic method, a get, which is unsafe because it has an unsafe callee from raw path. And another unsafe method, set length, it has no unsafe callee, no interior unsafe, but it is unsafe because it may break in some invariant of the required by the struct object. We also have an alternative way to define the struct. We can declare the constructor as unsafe and declare the get method as safe. In this way, because the constructor is always executed before the method, and this constructor has safety requirement, we can have some soundness criteria to always, if this criteria hold, the struct soundness is always a hold. We can have some criteria related to structure soundness. So what are these criteria? So if assume a struct is composed of constructors, static functions, method, and destructor, it is sound if the two conditions are hold. For the first condition related to the static method, which contains the constructor and other static method. If for all the program that use either the constructor or the static method, if the program satisfies the safety constraint of the method, of the static method, then the program does not lead to UB. So it is related to static method. And the second requirement is related to dynamic method. So for all the method and for all constructors, if a program uses the constructor and the method, and the program satisfies all the safety constraints of the constructor and the method, the program will not cause UB. So if these two criteria are hold, then the struct is sound. Based on the soundness criteria, we can also derive the encapsulation approach to achieve a sound struct. The first part is also related to the static method. If the static method has unsafe callee, the static method and its safety requirement should ensure the safety constraint of its unsafe callee are always satisfied. The second requirement is related to the second guideline about sound encapsulation is related to dynamic method. So for the dynamic method, then for all the unsafe callee of dynamic method, if given the invariant of the struct and the breaking invariant by some disruptive method, and the safety constraint of the method and the method is itself, if it satisfies the safety constraint of all its unsafe callees, then we say the encapsulation is sound. So what is the invariant and the breaking invariant? We will illustrate in this slide. So what is the invariant? It means a property that all constructors can ensure. There are also some minimal invariant according to the safety promise of Rust. If it is a reference or an instance, the minimal invariant is allocated a line because the object must must be aligned related to the tab, and the object must be initialized. So there are several minimal invariant that is always hold. Besides, if the struct has some extra safety invariant, the invariant may be broken by some method with mute self or reference mute self. And we we denote such broken invariant with BI. So several strat may have several such disruptive method. So this is a general approach for verification. It's only the theory part. Next, I will introduce our current practice of verification. So the practice is based on our tool, RAPx. It's a static analysis platform for Rust. RAPx has two layers, a core layer that is composed of the fundamental program analysis modules, such as alias analysis, range analysis, data flow analysis. And we have also, based on these core modules, we have upper level applications such as performance bug detection, robustness, and soundness verification. So our verification is also based on these core modules. The verification have 3 steps. The first step is to annotate the unsafe functions with safety tags. We have already introduced this part. The step 2 is to extract the audit unit from the target crate or module. Step 3 is to verify the soundness of each audit unit. So what is the concept of audit unit? Each audit unit has a set of soundness requirements to be verified. If all these requirements are satisfied, then the soundness of the crate can be verified. So this is a general concept of audit unit. So how to extract audit unit based on for the target crate? We should model the unsafety propagation first. We model it with as a UPG, which is unsafety propagation graph. So the UPG consider both function calls and instance flows. It is very similar to the call graph, but we also consider the instance flows, structured instance. What we do not consider is the function calls with safe callee, because we are not interested. There is no such encapsulation requirement with respect to safe callee. Let's use the strata VAC for demonstration. So in this UPG, on the top layer, we have a set of constructors of VAC. We have 10 constructors. The left 6 are safe, and the right 4 constructors are unsafe. They may also have unsafe callees to the external dependent API, unsafe APIs. And in the middle part, we have a set of methods of VAC. We have a safe method, unsafe method like set length, and private method like append elements. And some methods also have unsafe callees. So this figure shows how the UPG looks like. And then we can extract audit unit based on the UPG. There are 3 cases. Case 1 is all the dependent unsafe functions or method. They are leaf unsafe functions, like the following 6 unsafe functions. They are from external part. They are not within the struct. So they should be annotated with proper safety constraint. Obviously, this safety constraint should not be empty. And to verify the soundness of the encapsulation, we should assume all the safety constraints are sufficient, which means the unsafe function is sound. These 6 unsafe functions should be sound. In case 2, it concerns about the function encapsulation, which means the function has unsafe callees. We have 6 function calls of this case. For such case, for all the unsafe callees of the caller, we should check whether the function and its safety constraint satisfies all the safety constraint of the unsafe callee. If so, then we can verify the soundness of the caller. If not, either there are soundness issues, or there are all the safety declaration of the caller are insufficient. So we can use this to verify the consistency of the safety tag annotation. Case 3 is the most complicated one related to struct. We should examine whether each method with unsafe callee is sound. A soundness requirement is related to method encapsulation, which we have introduced. The environment of the constructor and the breaking environment, safety constraint of the method, and the method itself. Given such condition, the safety constraint of the unsafe callee of the method must be satisfied. So in this case, the target method is into a raw path with alloc. We should ensure the callee PTR rate is satisfied if consider all the 3 parts. Okay, we can further separate case 3 into 3 segments. The segment 1 concerns the constructor. So if the struct may have extra environment specified by developer, there are minimal environment provided according to the safety promise of Rust, but there may also be extra environment. For example, for VAC, the environment may contain the length of this field is less than or equal to buff dot capability, and the buff must be properly initialized. If this is the case, we should verify all the constructor can ensure the safety environment hold. And we should also analyze the breaking environment by consider all the disruptive method. It's a union of all the breaking environment. When analyze the breaking environment, we should also consider the safety constraint of the unsafe method. For example, set length may break in the environment of this length is smaller than or equal to buff.cap, but the safety constraint may require the developer to use it properly to maintain the safety environment. So in this case, the environment remains preserved. Okay, in this case, we can prove the soundness of audit unit. Why? Our audit unit approach must be sound. Why? Because according to the definition of the soundness criteria of struct, it has 2 requirements. All static method encapsulation should be sound. We have already extracted all such function calls with unsafe callees, and we should audit whether the safety requirement of unsafe callees are always satisfied. And the second requirement is about dynamic method. We also extract all such audit unit related to dynamic method. This is satisfied by case 3. Okay, so the last part is about how to verify the soundness of each audit unit. And this part is still under heavy development. So I will give some brief idea. Suppose the verification target is into raw path with alloc. This is the function we are trying to target in the verify std task. It contains 1 unsafe call set related to PTR rate. We already know that this PTR rate has 4 safety tags. And then we have to verify, because it's safe, we have to verify that the 4 tags can be satisfied by the method. Our verification is based on the MIR, so we can generate the data flow graph based on the MIR. Here we can find the PTR read, which is the unsafe function, and we can trace all the data flow related to read. And if we trace it here, it's it's a function call of allocator. It's a function call, so we can further obtain the data flow graph of this function like this way. And if we continue trace, and here the return value is also related to another function called allocator. So we continuously extract the data flow of this function call, and we finally find that it's a reference. So if we can abstract the data flow graph in this way, the parameter of the function is self, and it propagates to me, and then to me.allocator, and me.allocator is essentially self.buff.allocator. And through the PTR read, the result is alloc. The result is alloc. Okay, next we show how we can verify the first three properties: a valid PTR align and init. To verify these three properties, we trace the data flow backward until the constraint can be satisfied.
Brief note: we are at 45 minutes, so not sure how much longer this is going, but it would be good to have some time at the end for questions
I have
as well.
two pages left.
Okay, thanks.
Okay, thank you. So we first tracing the data flow backward, and we find that 14 is a reference. So according to the assumption of the invariant of object, raster object, if it is a reference to the object, then it must satisfy this three minimal invariant. So this is what this instruction can provide. Then we do forward analysis to check if the safety invariant can propagate to the parameter, and if the property is invalidated. Here we only have one instruction, and we can design a rule like this because X satisfies these three safety constraints, and Y is an operation. It's an address of dereference of X. So Y can derive these properties. So Y satisfies this safety constraint. So there are two steps. We first tracing the data flow back, and then do forward analysis to check if these properties are invalidated. And the last property is alias. So alias, we have to check it's a hazard. So we have to use forward analysis to check if the hazard is eliminated before the function returns. There are two conditions to check. There should be no mutation performed based on shared reference, and no shared mutable reference exists after the function returns. Our analysis is based on the alias analysis result. We have alias analysis module implemented based on the meet over passes approach. It's an over approximation, and it's also precise. And we can find all the alias of this 12. And then we have some rules because they are not mutated before the function returns through these aliases. So the first condition hold. A second condition hold because first the return value are not aggregated with others as the return value. So we only move 12 to 0. So we only return one instance. And the function parameter is ownership. So it is consumed. So after function return, there is only one reference to the object. This is the last slide. We would like to have some discussion related to the soundness of our verification approach. First of all, our audit unit extraction-based approach should be sound because we have provide the soundness criterion and show they satisfy all the criterion. And when verify the soundness of each audit unit, the soundness depends on two aspects. The first aspect is how we abstract the different instructions and do interpretations, and which is currently still under development. And we know we have a lot of work to do related to rigorous design and formal proof. And secondly, it is related to the underlying analysis model. Especially the alias analysis and data flow analysis and range analysis. Our current implementations are best towards over-approximation. However, it is not guaranteed to be sound. So we are designing test suite to evaluate the soundness of each module and continuously to fixing bugs if there are issues found. Okay, that's all of my presentation. Thank you.
Thank you very much, Professor Xu, especially for taking the time since it's 2 a.m. for you. We very much appreciate your time. I think that there were questions. I know Bart had a question earlier, and I suspect that there are a few other questions in the room. I see Ralph as well. But I think we'll start with Bart just because he's been waiting patiently. So
thank you very much. Thank you very much, Professor Xu, for giving us this nice presentation so late in the night. So one question I have is, are you monomorphizing during your analysis? And if not, what if your data flow that you're considering involves a trait method call on a type parameter? Because you seem to be unfolding the method calls, right? Like the allocator call, you're looking into the definition of it. What if that's a call on a type parameter and you don't know which type it is?
Okay, we are currently solve the problem case by case. We are still in this phase. For this example, to check if the hazard of alias can be eliminated, if this object, if this tab, the type of the allocator is copied, then we can directly know the header can be eliminated because it guarantees safe. It's a precondition. It's an optional sufficient condition. But our current analysis, we do not assume that we only use the minimal information of the tab. It should be sound. It should satisfy several safety properties, and if there are trait bound related to the tab, of course we will consider the trait bound. But currently we have not tackled issues related to trait bound. Our current method is to treat the trait bound method in the same way as the method of general struct. So if the struct implement the trait, so we directly integrate the trait method into the method of the struct.
Thank you. I have more questions, but I'll first leave the floor to others.
Go ahead, Ralph.
I guess I can go next. Yes, I also have many questions, but I guess we won't get through all of them here. Yeah, first of all, thanks for staying up so late. It's much appreciated. I know time zones are terrible, so thanks for sharing your tool with us. I have a question about this last example you showed. So you briefly could you go to the slide? You had the source code of into raw parts with alloc on the slide briefly. A few slides back. Yes, here. So one of the things that is crucial for soundness in this function is the very first line where we are wrapping self in manually drop. Right? If we remove that line, if we just make it let mute me equals self, then this becomes unsound for well, it no longer satisfies its spec. That's a bit more tricky. It also becomes unsound because you end up dropping the allocator and then also duplicating the allocator, right?
Yes.
So, and in your analysis of why this is sound, you never talked about this manually drop. So, like, where does this come in? It's very important somehow that this is checked. Right?
Okay.
How does the tool find the bug if we remove this?
Yeah. Actually, but already on the GitHub already raised similar issues to us. And if there is no manually drop of self, we should say something like drop 1, because 1 is a parameter. We can say drop 1 here. Drop 1, it's an instruction. So it means we modified 1, right? So 1 is an alias of 12. According to our analysis, 1 is an alias of 12. Oh, so it's an alias of self. So they are shared mutable alias. So for shared mutable alias, if you mutate through 1 reference, then it is UB. This is a rule.
Okay, so if there's code that uses shared mutable state correctly, you would not handle that. Basically, that's part of the approximation.
Sorry, can you?
So thanks for the. I think I understand this example. That's nice. But like not all shared mutable aliasing is UB, right? There are ways to do shared mutable aliasing with raw pointers, which is actually correct.
Are you asking question?
Well, I guess I'm asking what exact, like you said, if you detect shared mutable aliasing, you flag this as undefined behavior. So that will also, that's approximate, right? Like there is code that would be correct that doesn't actually have undefined behavior that your tool will say has undefined behavior. Did I understand that correctly?
Yes, we will give all the rules that like this one, no mutation is performed through shared references. We will check if all the if there are mutation operations through these aliases. If so, then we will give we will say that there may be some UB, so it is not verified. It is unsound.
Okay, thanks. I'll leave the floor to others if there's more questions.
Yeah, there was one question in the chat from L saying, thank you for your presentation and your time, Professor Xu. You mentioned that your verify std progress is at 90%. Are you hoping to reach 100% before the RFC is merged? Can the RFC be merged before 100% coverage?
Do you mean this result?
Yes.
The STD. Okay. So currently we don't support 2 types of issues. The first one is some logical environment, which is related to the feature of the function. So it's very difficult to represent, to abstract. And the second one is related to like the environment issue. Although we can achieve 100% coverage, but the safety tag we cannot represent it in this way. So they cannot be expanded to contract for verification. So we haven't count such safety functions, unsafe functions at the current stage. Maybe in the future we can have some coarse-grained, but yet useful for verification in the future. Maybe we can improve. That's why for the Rust for Linux, we are still facing very large challenge.
Yeah. Okay, I think I understand. So the challenge here is for functions where they have a lot of assumptions about the environment that they're being called in, perhaps, right?
Yeah, okay. It's very difficult to abstract with one tag. And we also want the tag to be expandable to contract. It's very difficult.
I understand. I think we might have time for one more short question. Bart, I don't know if you had a question, a follow-up to your previous question or something.
I have a bunch, but one slide 47.
Bart, I can stay with you if you would like to talk more.
Oh yeah, that'd be great.
Yeah, I should say we're happy to go over for a few minutes. We really don't want to hold you up any longer than you're willing, of course, but I'm sure that there are some more questions.
So I was intrigued by init buff tlen. I think that might be a typo because buff is a rawvec. It's not a pointer, right? You mean the buff dot inner dot ptr probably or something like that.
Okay. Here.
And so the after that one, right?
You mean this dot?
No, I mean init of buff, comma t, comma len on the same line.
Okay, here?
Yes. So buff is a rawvec. Buff is not a pointer.
Buff is a ref.
No, but buff, well, I don't know what you mean by buff. So here it's also a field of vec, right?
Yes.
And it's of type rawvec.
Mm-hmm.
It's not
so the rawvec must be initialized.
But here you're using the syntax that I expected for a pointer of len elements of type T.
Mm-hmm. Okay. So you thought buff should be a pointer.
Yes, I expect
according to the grammar. Okay, but here
the question is, what is init? How does init work in general, right?
Okay, this invariant part we are currently we haven't designed the grammar because we don't know what invariant might be introduced. So it's currently unrelated to safety tags. So safety tags are only currently are only related to unsafe function. So this is an invariant of the struct. We are still working on how to define the grammar related to such invariant.
So you're not really ready to state the invariant of vec at this point. This is an approximation. This is a sketch of what it would look like.
Yeah. Yes.
Because I think you also want to say that rawvec is kind of consistent internally, is a valid rawvec value. And furthermore, that the buffer that it points to is initialized for T elements or len elements of type T.
Yes. This is only a sketch. We would like to tackle the problem in the future. So because this problem is unrelated to this method is unrelated to the invariant. So I haven't provided more details related to that.
Right, because, well, of course, an unsafe caller of this method could rely on the properties stated by the invariant of the vec, right? But you don't prove post conditions, of course. You don't do anything for unsafe callers. I mean, you don't try to modularly, if there's an unsafe caller, you will analyze it separately. You will not try to use a post condition of this function to verify the caller.
Do you, okay. Do you mean other, if the method is other unsafe method?
So, I mean, so here you're verifying vec, but suppose now that I'm verifying some unsafe code that uses vec.
Use vec, okay.
And it will rely on the properties of the result value of into raw parts with alloc, right? But that would be a completely separate verification or analysis run that doesn't reuse any results of this analysis that you're doing on that method here.
Because according to our approach, we assume all the undefined behavior only originates from this unsafe code. So if we encapsulate it as safe, so no matter how other callers use a safe method, So it is guaranteed to be safe.
Well, actually, on that point, what if I return 2 copies of alloc, right? What if I do 2 reads of alloc and then return both of them? Nothing unsafe happens in this method, but callers will, even safe callers, will be unsafe in general. Will have a UB.
Okay, for this function, it is UB. We can detect because PTR read will introduce the hazard, the safety tag. Remember that the safety tag of alias.
A hazard, yes.
So if you have you return, like here we return move 12. If you have another allocator, maybe move another value, so you return 2 reference to the allocator. So it's UB because no shared mutable reference.
Why? No, it's not mutable. It's an immutable reference, right?
It's an owner. PTR 12 is an owner. This one is a reference. We read the memory pointed by the reference.
So these are, so now you're returning 2 allocator values or A values of type A. How do you know that's a problem? Because you're not monomorphizing, right? So how do you, which property exactly is being violated there?
This property, no shared mutable reference exists after the function returns. They can be further break down into 2 rules. The return value should not aggregate multiple reference because it returns 0. 0 currently aggregate 1. But if you aggregate more, like we replace copy 6 into another with another allocator, so it triggers the UB detection rule.
But it's not inherently UB, right?
We don't know.
That's the same thing I asked about earlier, right?
Yeah.
About being approximate. I'm a bit more confused because 12 is not a reference, right? 12 is something of arbitrary type A.
Yes.
So your notion of reference is a bit more general than just reference type, I guess. Like, what do you consider a reference?
It means because 13 is a reference. It points to a memory unit. Then we copy the memory unit to like 2 allocators, 12 and another allocator. This allocator may contain reference or pointers, and they point to, we have 2 objects that point to the same memory. So it's
you're
a
now
problem.
You're now hypothesizing about what type A actually is?
In worst case, so if A is copy, then we are okay, no UB. But we don't know A is copy. In general, A is a global allocator, so it's okay. There is no UB. But we don't know what A can be.
So you apply your rules for references because A might be a reference.
Because A might be a drop trait, may implement drop trait. So if A implement drop trait, so it's a problem.
Right.
Like,
so a more general question, you haven't written up, there's no paper on your verification approach yet, right?
Yeah, we are still developing this part.
Right.
It's very difficult.
But you do feel it's ready to be considered as a tool for the verification contest?
Because we think on one hand, it's a novel approach, especially designed for Rust. It's very different from traditional contract-based approach. So I think it's valuable to promote such an approach. Secondly, we have done the audit unit extraction part, and we can show that this part is sound. So our approach is sound. So the rest part is how to design the abstract interpretation rules and improve the precision of our underlying alias analysis algorithms. And I think these are it's a long, in the long run we have to we may need many time towards this goal to make the tool perfect.
Thank you very much. I'm not going to ask any more questions right
Okay.
now.
Thank you, but I would like to clarify one thing regarding our pull request in the verification STD. Our current implementation is not based on this version. So in the current submitted version, we recursively we do not verify use the invariant of the construct and breaking invariant. Instead, we verify all the paths from each constructor to the current method. Instead, we in this approach we can it's more advanced. We can have separation. We can same method. We consider constructor as one unit, and so we are still improving. But all the method, all the approach, they should be sound.
But aren't there infinitely many possible paths? Because you don't know what the client does, right?
Mm-hmm.
So how can you check all paths if there's infinite, like?
Okay, this is the most difficult thing in the past, but we think we have already figured out. Traditionally, in the past, we think we should enumerate all the method combinations. Obviously, it's impossible. But then we find that the broken invariant can only happen if the method has mute self parameters or reference to mute self. Then we only need to check what properties, if they break some properties. And then we can union all the properties they break. And from this invariant, so we minus that breaking invariant. So then this is a remaining invariant that can be guaranteed. When reaching, no matter what is the sequence of method call, it can be ensured, always ensured.
What if the type uses interior mutability or raw pointers? I mean, you can have mutation in ampersand self methods if you want to.
Mm-hmm. Do you mean there are extra code besides the method of the struct?
I think the question was that you say that you can only have a breaking invariant when you have like an ampersand mute or mute self method. But using interior mutability, you could do the same thing with just an ampersand, like an immutable reference to self.
Yeah. Yes, that is a problem related to the runtime checking. We haven't considered that yet.
And even without interior mutability, right? With raw pointers, I can also do that. Like inside vec, and a vec ampersand self method. I mean, it would be terribly unsound to do so, but only with the right callers would you actually get UB. Like if you mutate things behind the pointer indirection, that can be correct in some cases. So only checking the ampersand mute self methods, it seems a bit tricky.
Do you mean the parameter of the method is a raw pointer?
No, the parameter is ampersand self, but the struct contains as a field a raw pointer pointing to some other memory, and then the struct can mutate that memory. Right? Like here, the get method might mutate star PTR, for example.
Do you mean who mutates PTR?
I can add a method fn get to.
I added an example in the Zoom chat, for example.
Okay.
Yeah, something like that.
To mutate PTR. Then
to mutate what PTR points to.
okay.
Right? Not to mutate the field itself, but to mutate through the field. If you can see the Zoom chat, I'm not sure if you can see the Zoom chat in while you have the screen shared, but Xavier just posted an example.
Okay. Where can I find? In the chat. Okay.
Yes.
Yeah.
Okay. Star. Okay. So this is a raw pointer dereference, right?
Yeah.
Yes.
So the raw pointer dereference also has a safety constraint.
Yeah.
So we should ensure that from all the passes to the method satisfy the safety constraint of the raw pointer dereference. They are uniform across all call set for raw pointer dereference.
Yeah, but the constraint would be something like the pointer is valid and points to some memory, right? So that would be satisfied. That would be fine.
Mm-hmm.
Yeah, the question here would be like with your breaking invariance, right? Like imagine if raw pointer was like the capacity of your vector or something like that, right? Like if you're mutating that could be breaking the invariant of vec.
Okay.
And you need to somehow reflect that, right?
Yes. Yes, I think I get your point. Thank you, Ralph, for raising this concern. I think you are right. We can mutate through the raw pointer. Yeah.
I have one other question, maybe. Or did you want to? Sorry, I don't want to hold up everybody else. Everybody else should feel free to leave. I just want to use the opportunity to ask questions. You had this slide. So I was wondering about the meaning of all of these safety tags. You had the slide where you had them in a table, I think, but it was a bit fast for me to follow. Right. So this is okay for me. For some of them, it's easy, like alignment and sizes and all that stuff. But the things which refer to stuff happening in memory, that seems to presuppose that you somehow you have to have some model of how memory looks like. And that's of course in Rust in general. That's not an the Rust operation semantics team is still deciding on how those things will look like. So like what is your memory model?
The memory model, we currently only expand the safety tags, and we describe the meaning of this safety tag. We haven't thought about a detailed memory model yet.
But you have this mem function object. I don't know, this mem thing here. What is mem? What is the type of mem? What data does it contain?
Okay. For example, for valid string, then we check. We give a parameter related to the address range. Then the memory is an abstraction of the valid UTF-8 format. So we have, for contract, we have to write such valid UTF-8 function check by ourselves in order to prove. For the C string, so the last unit of the memory, p plus length, 2p plus length plus 1 should be empty.
So this is like so this mem function returns a byte here, or what is the?
Yes, the byte. Yeah.
And what is your what is a byte for you? Like, do you model uninitialized memory? Do you model provenance on bytes? Like, how far does this go?
Okay. This part is related to the abstraction interpretation part. I think I will give more concrete answer maybe in the next talk, if possible.
Okay. Yeah, that sounds
we can
like
also move some of this discussion async to a Zulip thread, for example, so that you can have the opportunity to respond when it's more convenient.
Okay.
Ralph, I don't know if you have any further questions, but
oh, it's okay. I think I want to give you some chance to sleep as well. So.
Yeah. So unless there are any last questions from anybody else in the audience, I think we'll bring things to a close for today. All right. Well, in that case, thank you very much, Professor Xu. We were very glad to have your talk and to learn a little bit more about your tool and the safety tag work. And we hope to hear more from you in the future.
Thank you. Thank you, guys.
Right. We'll see everybody next month for the next RFMIG talk. All right. Bye.